Hello everyone. Today we are going to learn the basics of RTL verification. And before jumping into the topic, let's see few things about this VLSI design flow. In a VLSI design flow, the first step is design specification. The second one is design partition. The third one is design entity. This design entity means writing the RTL code, or Verilog code. Once the code is written, the next step is functional verification. This functional verification can be written with the help of either RTL, that means either Verilog code or system Verilog code. Okay. So what is this functional verification? See, already we wrote the code. So this code and the behavior of our circuit should be same. Okay, that means the RTL behavior and the specification behavior should be same. So if RTL equal to circuit, then that is called checking this one whether RTL equals to circuit or not, or the behavior of our specification, the specification that we have mentioned, both are same or not. That step is called functional verification. And for functional verification we write Verilog code. That is, in functional verification what we do, we write the test bench. We write the test bench using Verilog or system Verilog. Okay, so the next one is why this functional verification. See, all these materials actually I have collected from a website. You might have heard, this is a wonderful website. Okay, this is called TESTBENCH.in. It has plenty of resources related to Verilog, or we can say RTL or system Verilog. All these materials belongs to this website. Okay, TESTBENCH.in. Why functional verification? Because if it is done, the functional verification is done without any error, then it builds the confidence and we stay in business. Okay, see, all these lines are self-explanatory lines. Okay, self-explained. A simple purpose for functional verification is to detect the failures or error or bugs. It can be identified and corrected before it gets shipped to the customer. That means before the IC is designed, we want to detect the failures or the bugs. It should be identified. Okay, if RTL designers, those who write the Verilog code, makes a mistake in designing or coding, then this results as a bug. So if while you are writing the Verilog code or RTL code, if there is any kind of error or mistake, that mistake is called bug. Okay, and if this bug is executed, in certain situation the system will produce wrong results. That means if bug is there and if it is not resolved, that means no one detected that one, then it will produce wrong results and causing a failure. Okay, then not all mistakes will necessarily result in failures. The bug in the DAD code will never result in failure. DAD code means the code that is never executed. Those type of codes are called DAD code. Okay, for example, there are this 1 2 3 4 5 number of codes are there. These 3 codes are executed, but this 2 code, the 2 lines of code, it never got executed. Then the whole program, then this line is called DAD code. Okay, this is, and if even if there is a bug here in this DAD code, but it is not going to cause failure, right? Because this 2 line never got executed. A single mistake may result in a wide range of failure symptoms. Okay, not all the bugs are caused by coding errors. Because of some other reasons also, the bug possibility is there is a presence of bug. Okay, there are possibilities that error may in the specification itself. That means in the VLSI design cycle, maybe there is error in the specification itself. Okay, sometimes miscommunication between the teams here means those who are writing the code, those who prepared this architecture, or those who prepared what do you call, those who designed the physical design part. Or so if there is some kind of miscommunication between the team members, then it may lead to wrong design. That you have to understand. So it is all about why functional verification is needed. Then for functional verification, what we use? We use Verilog or system Verilog to write a test bench. Okay, then what is a test bench? This checks whether the RTL implementation, the RTL code that we wrote, meets the design spec or not. Okay, so we are checking here, we are verifying here, okay, by writing the test bench. So test bench provide an environment, okay, it provide an environment to check the RTL implementation and the design spec are same or not. Okay, so it provides an environment. This creates invalid and unexpected. See, this test bench environment, it creates both valid and expected condition as well as invalid and unexpected condition to test the design. What is the meaning of this one? Let's see, this is a counter. Okay, this is my clock, this is my output, and this is my, let's say, input. So every passage of clock, there should be one count. The count must increase. Okay, so this is my valid condition, right? So in the test bench, what, even if invalid condition you can apply, like you give neg edge of clock, that means not passage. We know that on the passage of clock the count should increase, but what about the negative edge of clock? So you have to, we can test even this invalid condition also, because what will happen, our expected is this one, on passage of clock count should increase, and if negative edge of clock comes, then it should not increase, right? That is what our design, our circuit demands, right? But in case if there is a bug, and suppose the transition happen, the trigger happens not on the passage of clock, let's say on the neg edge of clock. So what do we do here? This is an invalid condition, right? Neg edge of clock, it is an invalid condition, but still we want to check this one to detect the bug. Okay, so that bug can be detected. So here this test bench environment, it not only detects valid expected condition, so even we can give invalid and unexpected condition to test the design. Okay, there are different type of test benches are there. Okay, linear test bench, linear random test bench, file input output based test bench, state machine based test bench, task based, then self-checking test benches. Okay, the first one is linear test bench. Linear test bench is a simple one. Okay, it is simplest one, it is very fast, and it is easiest way of writing test benches. But see, it is the simple one, but here it is the slowest way to execute the stimulus. I will explain what is a stimulus. Okay, and the linear test benches are written in the VHDL or Verilog language. In this test bench, simple linear sequence of test vector is mentioned. Stimulus code like this is easy to generate, translating a vector file with a Perl script, for example. Okay, this Perl script is used to automate the test bench. Okay, if you want to automate the test bench, then automation, that means Perl script is a automation language. Okay, small models, and see, this linear test bench is used when there is a small model or small design. Okay, the small design or small models can be verified with this test bench. And how it looks like this linear test bench, see, this is simple one. This is a adder circuit, okay, and this module, this is your design. Okay, we want to verify this one with this linear test bench. So it is also called DUT. This module, your design is also called DUT. DUT means design under test. Okay, then this is my test bench. So here we are instantiating this DUT. Then we are giving, see, stimulus means we are applying the inputs, okay, to test our design. That is called stimulus. Okay, applying the inputs. Then this is my input we applied, then B we provided. Okay, then we want to display, see, this is my adder circuit, so C equal to A plus B. This is the logic, right? So we want to display A, B and C. Send the output to terminal for visual inspection. This is end of the model. So this is simple one. Okay, this is called linear test bench. So to check small design, small design, we can use linear test bench. Okay, where stimulus or test vectors are applied to test our design. This is what it is written here. Okay, this part is simple linear sequence of test vector is mentioned. Stimulus code like this is easy to generate. Okay, then the next one is, and sorry, next, this linear test bench again. See, typically this linear test bench perform following task. What it does, instantiate the design under test. This is what is instantiating the design under test. This is instantiating. Then the second one is stimulate the DUT by applying the test vectors. That means we are applying the test vector like this. This is my stimulus we are applying here, or we can say test vector. Third one is output. It output results waveform window or a terminal for visual inspection. Like you want to check this one, you know, test the design, then either waveform view you can get or your visual inspection, like display A, then B, then C. Okay, so these three things we achieve with the help of this linear test bench. To test all possible scenarios which are known to us, it is not an easy task. Okay, development time increases exponentially as the number of scenarios increases, and maintain them is nightmare. Instead of listing out all the possible scenarios, pick up some pick up some randomly and check the DUT. See what we did here. How many inputs we provided here? Just two inputs, A and B. Okay, this is 45, then 12. But there are so many numbers, right? We can give here, right? 1, 2, then 3, 4, 5, 6, 7, 8. This is 16-bit number. 2 to the power 16 number we can apply here, and here we can get 2 to the power 16 number. But here only we applied two number of stimulus. Okay, so we did not check here. We did not check other inputs, other test vectors. Let's say let's provide A equal to -3 and B equal to -6. Then what will happen? If we provide A equal to, let's say, some kind of 0.1 and B equal to 0.3, then what will happen? So these are all test vector we can verify, and whether we are getting the correct result or not, we can verify. Okay, this is what it is saying. Okay, so if you want to test all these things, all this scenario, then it is a nightmare. The development time increases exponentially. That means one by one you have to give. See, that means A equal to this one, B equal to this one, you check this one, then A equal to this number, B equal to, so A can be 2 to the power 16 number, and B can be 2 to the power 16 number. Then if you all this combination, if you want, you can check. So this is going to take time, right? So what we do here, so see, so instead of listing out all the possible scenario, pick up some randomly and check the DUT. So this can be done with the help of this linear random test bench. Okay, so what we do here, random test bench, it doesn't use hard code values like linear. See, hard code values means we provided a equal to, see, it is visible here, right? A equal to this one and B equal to this one. But in case of linear random test bench, we don't do like this, like a equal to this one, b equal to this one, then you check this one. We don't do this one. Okay, so here we don't use hard code values like linear test bench. Input stimulus is generated using the random values. So there is a construct in Verilog, that is a system function called random, $random. If you type this $random, then what it will do? Randomly it will generate numbers that we also don't know. It is system defined, these numbers. So instead of checking all these numbers one by one, a equal to this, b equal to this, what we can do here, we can use this system function random. Okay, provides a mechanism for generating random numbers. The function returns a new 32-bit random numbers, and each time it is called. So every time it is called, it generates one random number that is not known to us. Okay, these test cases are not easily readable and also not reusable. So what is the disadvantage of this linear random test benches? It is not easily readable and it is not reusable. Why it is not reusable? Why it is not reusable? Because this random, it generates random number, and this is what, because random number means, let's say a equal to 1, so next time it may generate a equal to 1000. So because of this reason, it cannot be reusable. Okay, so new tests have to be created when the specification or design changes to accommodate the changes. The main disadvantage of this testing is that we never know what random values are generated. That is what I said here. We never know what random values are generated. This is a disadvantage. Okay, and it may waste simulation cycles by generating some values, and probability is there. Let's say it generated a equal to 1. Maybe after 10 seconds again it generated a equal to 1. After 1 minute again it generated a equal to 1. Already we checked this combination a equal to 1, but if it generates the same combination again and again, then definitely it is a waste of time. Okay, so this is another disadvantage. So how it looks like, this linear random test bench, this is my same module, then this is my test bench adder. See, instead of writing a equal to here 5 or 6 or 7, b equal to 1, 2, right? If you write a equal to $random, then it will generate random numbers for a, 32-bit random numbers. Then b, 32-bit, it can be 1000. Or if you want to see this binary data, if you want to display binary data, 32-bit binary values. Okay, so here no need to give this hard code values like what we did in our linear test bench cases. Okay, then end module. So this is how linear test bench, random test bench is written. Okay, it is definitely time saving this one is, but still there are disadvantages are there. Okay, next one is file IO, file input output test bench. Here what we do, we get the stimulus. Stimulus means we get the input that we want to check. Okay, so we get the stimulus from external file, and what we do, then we are writing the output or the test results to external file. That means let's say you have already stored the stimulus a equal to 1, b equal to 1, a equal to 2, b equal to 2 in a text file. That text file we are getting. Okay, then whatever output we are getting, the C is the output here. So if C is the output, then we are writing that one into another text file. Okay, C equal to this one, C equal to this one. Okay, so this is what this is file IO test bench means. So this is one module. This is one module, read memory, and so see these are all sample signal. Okay, then this is initial read memory. We are reading the memory, and it is the data is in the text file. Then we are displaying contents of memory after reading data file. Then whatever data we are reading from the text file, we are displaying here. Okay, display this one. So this is what is all about file IO test bench. See, all these examples, I think it is available in the testbench.in. If you want to learn more about all these things, then please go and check this testbench.in. Okay, because if I will include all those examples, then definitely it is going to take time. So this is just to kind of let you know that these things are available, and if you want to learn more, then definitely there are sources are available from where you can learn. Okay, the next one is state machine based test bench. Okay, a state machine test bench use state machine to generate input vectors. Input vectors means the stimulus, the inputs that we want to check. Okay, and drive it to the IO ports of the design. One test bench can have multiple state machines, each handling a different functionality. So definitely it is, see, this is passage of clock, then it is state, read, then condition, then you do all these things. See here, address, again we used here this random function. Okay, then finish, then another state is there, write. So here one state is read and another state is write. So many number of state if you want you can include. So this is how this test bench, this state machine based this test bench looks like. Okay, so this is another type. The next one is task based test bench. Task based verification is more flexible overall the above approaches. So whatever type of this test benches so far we have seen, so this task based is more flexible. Okay, all the operations are done using tasks and functions. Okay, I will give you one example, this task based example. In maybe in the next video I will explain whole this, what you call this, how to do the verification using this RTL code. Okay, using this one, this task based test bench. Whole video will be on this topic only. Okay, task based test bench. The task based BFM is extremely efficient if the device under test performs many calculation. Then each task or function focuses on one single functionality. Verification of DUT using the task based test bench is faster. So this is to verify our design, we write the task here. The first task is write, then second one is read, then we are generating address using this random function, then we are data also generated using this random function. Then okay, so my next video will be related to RTL verification based on this one, task based test bench. And here I will explain one, I will write one complete code, that is memory, how to verify the memory. Okay, and we will see the simulation result. Not like that I will what do you call this, I will write the code on this PPT and I will show you. No, I will use the software, I will use the tools, EDA tools, and we will see whether we are getting the correct result or not. Okay, then how to check the results. See, how does a verification engineer check whether the results obtained from the simulation match the original specification of the design or not? For simple test benches like the above, output is displayed in the waveform. See, output, you can verify that waveform based verification you can go with, or this visual checking. Visual checking is the oldest and most labor intensive technique. The quality of the verification depends on the determination and dedication of the individual who is doing the checking, because this verification is not an easy task, because first design is done, then verification is done. This verification consumes more time than the design, and what usually it is said that this verification part, it consumes around 70% of your time, and the design part consumes 30% of your time. So this verification part is very, very crucial. Okay, that's why this verification engineer, they play a very important role in VLSI company. Okay, it is not practical to verify complex models. See, these things are very small codes. Okay, there will be thousands of lines, or maybe it is 10,000, 20,000 number of lines in a code. Okay, so it is not practical to verify a complex model. Okay, merely by examining the waveform or text file. It is not possible just by looking at the waveforms. You cannot verify, or just the text file that what you call this visual inspection checking, you cannot verify. Whenever a change is made to the DUT to add a new feature or to fix a bug, same amount of effort needs to be deployed to check the simulation results. That means if there is a bug, then you change the code, then again you have to check the simulation results. Okay, right? So definitely more efforts are needed for all these kind of checking. Okay, so there is self-checking test benches are available. Okay, what is this self-checking test bench is? A self-checking test bench checks expected results against actual results. Then what they will do? Then they will compare. Okay, so although self-checking test benches require considerably more effort during the initial test bench creation phase, this technique can dramatically reduce the amount of effort needed to recheck a design after a change has been made to the DUT. Debugging time is significantly shortened if the self-checking test benches are used, then debugging time is significantly less by useful error tracking information that can be built into the test bench to show where a design fails. A self-checking test bench has two major parts. One is the input blocks and another is the output blocks. Okay, input blocks consist of stimulus. See, this is what this self-checking test bench environment is. Okay, 4 blocks are there total. One is stimulus, one is driver, one is DUT, one is monitor. DUT already we saw. DUT means your design, your Verilog module. Okay, stimulus we already saw. Stimulus means the input that we are giving. Okay, so your self-checking test bench has two major parts. One is input blocks, one is output blocks. Input block consists of stimulus and driver. This stimulus and driver is called input block. Okay, and what it does, they drive the stimulus to the DUT. These two, it drives the stimulus to the DUT. Means it provides the suitable condition that has to be verified to the DUT. Okay, the output block consists of monitor. This is the output block to collect the DUT. So whatever DUT output, whatever the output after providing the stimulus, the DUT will give you the result. Okay, that result is shown here, monitor. So the monitor, what it does, it collects the DUT outputs and verify them. All the above approaches require the test writer to create an explicit test for each feature of the design. Verification approach, in which each feature is written in a separate test case file, is called directed verification. Directed verification means for every condition. Okay, that means let's say there are 100 condition, it needs to be checked. Okay, 100 expected results. So for this expected results, you have 100 number of condition that needs to be checked. So for 100 condition, we have to write 100 number of test benches. Okay, see, in this linear test bench, what we did here, see, we wanted to check this one. See, the linear random test bench, we want to check this one. So this is the only one single test bench for this one condition. Okay, so this random, what it does, it generates thousands of inputs, right? Random means 32-bit inputs. So single test bench can generate thousands number of test vector or stimulus which can be checked. Okay, but here what this self-checking test bench, what it does, for every condition there is a test bench, and that is called test case. So each condition that has to be checked is called test case. Okay, and this type of verification is called directed verification. Okay, the self-checking test bench, see, this is one example here. This is stimulus, driver, DUT, monitor. Okay, this is again the adder. This is your module. DUT. This is small, what you call, sample code. Okay, so this is my this test bench instantiation. Then this is my random. So this is if a plus b not equal to c, we are checking whether a plus b equal to c or not. Okay, then this is called monitor logic. See, this is called, these inputs are called stimulus, right? This is this stimulus. Okay, and this two provides this stimulus to DUT. So this stimulus is given to this DUT. Then what we are doing, the output of this one is called monitor. Not monitor, the monitor collects output of this one, DUT. Okay, so here what we are doing, this is the monitor logic. So what we are monitoring here, we are checking here whether this a plus b equal to c or not, and it will show, it will, if not equal to c, then it will check, it will show you error. Okay, so this is just a sample code, and in my next video I will write a, what you call this, there will be a memory, and we'll test that memory. Okay, I will show you how to test, how to write the RTL code to test the memory, that is how the RTL verification is done actually. Okay, and I will use the EDA tools, and we'll verify, and I will show you the process, the steps that is done and that can be done, and you can learn a lot of things related to this RTL verification from that from my next video. Okay, so this is all about the basics of this RTL verification, and though I explained only the basic part, and all these materials actually belongs to testbench.in. So if you want to learn more about all these different type of test bench, they have plenty of resources in their website, then you can visit this testbench.in. So thank you so much for watching, and if you really learned something, then you can like this tutorial, and you can also subscribe for more videos. Okay, so thank you so much for watching.